Welcome to the Science Enigma. Today we're delving into the mysterious and mind-boggling concept of spooky action at a distance and its connection to the possibility of a multiverse. So buckle up, because we're about to explore the intriguing world of quantum entanglement and its potential implications for multiple universes. Let's get started. To grasp the concept of spooky action at a distance, we need to dive into the weird and wonderful world of quantum physics. 1. Quantum entanglement, where two particles become interconnected in such a way that the state of one particle instantaneously influences the state of the other, no matter the distance between them. Quantum entanglement was famously challenged by none other than Albert Einstein, Boris Podolsky, and Nathan Rosen in their groundbreaking EPR paper. Einstein referred to this phenomenon as spooky action at a distance because it seemed to violate the speed of light limit set by his theory of relativity. Now, here's where it gets really interesting. Some physicists speculate that quantum entanglement might be connected to the existence of wormholes. Wormholes are hypothetical tunnels in spacetime that could potentially connect distant regions of the universe or even different universes. So, how does all of this tie into the idea of a multiverse? Well, there are several theories suggesting that quantum entanglement and the existence of multiple universes might be intertwined. For instance, the many worlds interpretation proposes that every quantum event spawns a multitude of parallel universes, each representing a different outcome. Let's dive into some examples of current experiments and the challenges researchers face in exploring the connection between spooky action at a distance and the multiverse. Some interpretations of quantum suggest that our entire universe is governed by a single universal wave function, constantly splitting and multiplying to create a multitude of new realities. It's a bold claim, so let's explore how we arrive at such a fascinating proposition. Our journey into the quantum multiverse begins with a fundamental realization: the wave-like property of matter. French physicist Louis de Broglie was a trailblazer in proposing that every subatomic particle possesses a wave associated with it. The particles, especially electrons, exhibited wave-like behavior in experiments. This concept, known as wave-particle duality, laid the groundwork for understanding the bizarre behavior of particles. Notably, when electrons scattered off a thin foil, their behavior was more characteristic of a wave than a particle, sparking intrigue among physicists. This notion led Schrödinger to develop his famous equation to describe the behavior of these matter waves, a mathematical framework still employed in quantum mechanics today. As the idea of a wave of matter gained traction, a fundamental question emerged: what does a wave of matter actually look like? Early quantum theorists, including Erwin Schrödinger, proposed that particles themselves were spread out over space in the form of a wave. Schrödinger's equation, though influential, faced challenges when put to the test in experiments. While it accurately described particles behaving like waves in mid-flight, it clashed with experimental results when particles reached a target. For instance, an electron, acting like a wave mid-flight, would land as a single, compact particle at the target, challenging the idea of it being physically extended in space. This duality dilemma, particles behaving like waves in certain circumstances but manifesting as particles in others, added complexity to the understanding of quantum mechanics. It prompted further exploration into the nature of matter and the dualistic behavior that continues to captivate physicists to this day. Instead of the wave-particle duality, an alternative interpretation began gaining traction in the world of quantum mechanics. Today, we know it as the Copenhagen interpretation, and it stands as the most widely accepted model among physicists. Let's dive into the essence of this interpretation and how it has reshaped our understanding of the quantum world. In the Copenhagen interpretation, the concept of the wave function takes center stage. Physicists refer to the wave function as the wave-like property of matter. However, in this model, the wave function isn't regarded as a tangible entity but rather as a mathematical tool. It doesn't physically exist. Instead, it serves as a convenient mathematical construct to describe a cloud of quantum mechanical probabilities. The Copenhagen interpretation introduces a fascinating perspective. The wave function isn't an actual wave but a mathematical convenience. It helps us navigate the intricate landscape of quantum mechanics by providing a framework to understand the probabilities of locating a subatomic particle at a particular position during measurement. While the Copenhagen interpretation has been a cornerstone in quantum mechanics, it grapples with certain challenges. As Schrödinger himself pointed out, the transition of the wave function from a cloud of probabilities to non-existence upon observation raises questions. Let's explore an alternative perspective that seeks to provide a more meaningful role for the wave function in our understanding of the quantum world. Could the wave function be as real as the particles it describes? Louis de Broglie initially proposed this idea, but it didn't gain widespread acceptance. However, some physicists, like Hugh Everett, revisited this concept, reaching a conclusion similar to de Broglie's. Viewing the wave function as a tangible entity resolves the measurement problem inherent in the Copenhagen interpretation. By considering the wave function as a real entity, we redefine the nature of measurement. In this perspective, measurement isn't a special process that annihilates the wave function, rather, it's a continuous interaction between quantum particles and wave functions. When electrons hit a detector, they're simply interacting with atoms, sending signals, creating electrical currents and initiating a cascade of interactions that extend far beyond the act of measurement. In this reimagined framework, every particle has its own wave function, and they all interact harmoniously. No longer is measurement a disruptive force, instead, it's an ongoing interplay of particles and wave functions. The tools of quantum mechanics, including Schrödinger's equation, become powerful predictors of their behavior in this dynamic environment. Let's understand quantum particles and overlapping wave functions. Quantum particles possess a fascinating property thanks to their wave functions. When two particles interact, their encounter is not a simple collision. Instead, their wave functions momentarily overlap. During this overlap, a remarkable transformation occurs. Two separate wave functions cease to exist, giving rise to a singular wave function that intricately describes both particles simultaneously. This process of wave function overlap leads to a phenomenon known as quantum entanglement, a term coined by Albert Einstein, who famously referred to it as spooky action at a distance. Even as the entangled particles part ways, they maintain this unified wave function, connecting them in a mysterious and instantaneous manner. As we follow the intricate steps of a measurement, a cascade of entanglements unfolds. An electron becomes entangled with atoms in a screen, which in turn entangle with electrons in wire, and so forth. Astonishingly, particles within our brains entangle with Earth, with every beam of light traveling to and from our planet. This web of entanglements extends to every particle in the universe, interconnecting in a cosmic dance. With each new entanglement, a singular wave function emerges, describing the amalgamation of all interconnected particles. This leads us to a profound realization: If we consider the wave function as a tangible entity, then there exists a single wave function that encapsulates the entire universe. The many worlds interpretation takes center stage when we examine the intricacies of observation in quantum mechanics. In this quantum landscape, the behavior of particles is uncertain. Sometimes they go up, sometimes they go down. The magic happens when quantum particles interact, causing the universal wave function to split into multiple sections, creating different universes for each possible outcome. The key to the multiverse lies in the entanglement of quantum particles. Every time particles entangle with one another, the universe undergoes a continuous process of creation, generating multiple copies of itself. These universes are nearly identical, differing only in the minutiae of random quantum processes. Picture this: there are countless versions of you right now, each watching this, yet diverging due to some tiny quantum detail.